let's continue. Now, we can continue now. You can try and finish those at home, okay? So, I looked up the proof. I want to show you the proof of the last rule, okay? Are you looking, Ben? So, imagine we have two springs like this. This is K1, and this is K2, okay? And then I pull in a force here, and it's moved a distance x, yeah? So, you know, here, each of these also, okay, so you know Hooke's law, F equals Kx, yeah? So that means here, the K would equal F over X, yeah? Now, here and here, the total force is from these two springs. So there's this one which is pulling to the left and this one which is pulling to the left. So this force here, if you want to think about it, if it's balanced, it has to equal these two. So that will be the first one, which is K1 x1 plus K2 x2 all over x. But the distance these move must be the same, otherwise it'd be at an angle. So what will happen then is they all cancel and you're just left with K is K1 plus K2. So that's the formula I gave you for when they're in parallel. And then the next one when they're in series. So if you move this a distance x, what would the force be here? So again, the same formula, K equals F over X here, right? Yeah, that's it. Okay, let me think. So that's, I have to cheat. I forgot already. I was just reading it. Okay. Oh yeah, okay, sorry. I'm so lazy. This one moves x1 and this one moves x2. So the x in total is x1 plus x2. This one moves x, this is x1 plus x2. And if we think about our formula f equals kx, then the x here is, like I said, f over k. And this one here would be f1 over K1, and this one here would be F2 over K2. And here, this, I think I told you this before. Remember, if we have a string and there's a force here, then the force here is also the same. If you have one piece of string, the force everywhere is the same. So it means that this F here would be the same as here, and the same as here, and the same as here, and the same as here. It's all the same. So these cancel, and you end up with 1 over k equals 1 over k1 plus 1 over k2. Anyways, you don't need to write that down. I just wanted to show you that it is true. Okay? So this website was helpful. Thank you. And now we'll continue with the electricity. Yeah, I'm going to continue though, but that's okay. Physics, electricity, charge and current. Let's get a start here. Be strong. Be strong. Too tired?
No, I just heard that title. I got headache.
Charge and current. Okay, did you write that down? I'm so hungry.
Hungry too.
You too? What you have for lunch?
It's in the restaurant, school restaurant. know the burger?
Yeah?
That big.
Terrible. Terrible. Any chips?
Yeah, a little bit chips. And
Okay.
that cost me €4.50. That small burger.
Disgraceful. Okay. Charge and current. So from chemistry, or middle school even, you may remember that electric charge is a property of electrons and protons. So you remember electrons have a negative charge and protons have a positive charge. But you know this. This is for babies. You know this. Things that are negatively charged and things that are positively charged pull on each other. This makes the electron and the proton stick together to make atoms. Things that have the same charge, they push. So like proton and proton, they move away. Electron and electron, they move away. Okay. They repel. You know this from chemistry, right? So you don't need to write this down. You know this. Law of charges. Okay, so this is our first physics definition. We say a current is the flow of charge. Whoops, sorry. Come on. So for example, if I have an electron, or no, let's say I have a proton. The proton moves, I move the proton from here to here. I call that a current. So if I have charge, and the charge is moving, then I say that's a current.
So the length is current?
No, like the flow, you know.
Speed?
It's like a speed actually, yeah. Yeah, because the unit will be charge per second. How much charge per second. So it's like a speed. Yeah. So current is the speed of the charge nearly. Yeah. Now, I don't know, do you use this word in chemistry, current? Because we say that in a metal, the free electrons flow. So you know if you have a metal, the electrons move. You learned this from chemistry. Yeah?
Yeah.
Okay, so I'll let you write this much down. Here's a picture. You see what I mean? You did this in chemistry, no?
I think so.
You think so? I think you did.
I only got C.
Oh, well. Ben, do you remember doing this in chemistry?
In terms of this, I don't remember this word.
Current? Okay.
I have same idea. Maybe, yeah.
Same idea, okay.
Like delocalized and localized.
What's that? Delocalized.
Delocalized can produce electron inside metal, I say.
Delocalizes produces electrons inside metals. And then do the electrons move?
Yeah.
So this movement is called a current.
That is random move.
Depends. So
Okay.
if you have a piece of metal and you don't do anything, just a piece of metal, you just leave it there. You're right. It'll just move randomly.
Yeah.
But you can do something and you can make them all move in one direction.
Yeah. Yeah, I know.
Yeah, but naturally they just move randomly.
Yeah.
Yeah. No, Ben doesn't like when you use Chinese. He only likes when you use English. Right, Ben?
Actually, I don't know this mean.
Which meaning?
But I think you're correct. It is A or something.
Yeah, A. Amp. Yeah, we'll do that in a moment. Yeah. Continue? Ampere, yeah. Yeah. Okay. Now, an electrolyte is a chemical that produces a current. It's used in batteries to make ions flow, producing a current. You know what ions are? Yeah? So you don't need to write that down. So here's a picture.
This is
I know. Don't worry. We don't have to study this. We only need to know the word. Okay? So this here, H2SO4, this is an example of an electrolyte. Because it lets the charge flow. So here, this is negative goes here, and positive goes here.
Yeah.
This is called a current.
Yeah.
And this material here is called an electrolyte.
Yeah.
Because the ions flow. Did you do this in chemistry with Lorraine?
No, not here.
Not yet. You can just write this down.
Right there.
Oh, be strong. Be strong. What's wrong, guys? Okay, continue. Okay. So, which way should we say the current flows? So, if you look at this picture, here's the battery,
Oh yeah.
here's the switch.
Yeah.
Do we say the current goes this way?
Yeah. Yeah. Yeah.
Or do we say it goes this way?
No.
I can't remember at all.
You can't remember. Positive to negative?
It's
Negative to
from-
positive?
It's from positive to negative.
Well, it kind of, it's not so clear, but you're right. It's usually positive to negative. But I just want you to be very, very clear. We say that the current goes from positive to negative. You're right. However, the electrons,
Oh yeah.
you know this,
Yeah.
the electrons move from negative to
Yeah.
positive.
Yeah.
Now that's bad English. We say the current flows from positive to negative, but the electrons move from negative to positive. So the normal current is positive to negative, but the electrons are negative to positive. If an electron moves from A to B, we say there's a current from B to A.
Yeah.
Yes, B to A. That's correct. Now you have to be careful about that, okay? I think it would be helpful if you draw this picture.
Long time to enjoy this kind of.
Yeah. It's not so bad, really, it's not so bad. I promise. Be strong.
In high school, we kind of practice for solving this kind of picture, and still don't understand.
Don't worry. You're in my class now. Maybe it'll be better. I didn't wish you last week Happy Women's Day.
Okay.
I forgot to say Happy Women's Day. Because Joan told me, Ben, you wished her Happy Women's Day last week. Which I thought was good.
Is that a scooter? scooter is a good idea.
Scooter?
Just
Yeah.
in here, because I see lots of people.
Lots of people have them. I have one,
Really.
but I use my bicycle now.
Is
But I
that
have a scooter.
safe?
I used it for about 1 year before I got my bicycle, and I felt it was safe. Are you getting electric scooter?
I won't get electric.
Yeah.
That's more faster.
Yeah, now just be careful, okay? Just so you know, there's a limit. Maximum power is 250 watts, and maximum speed is 25 kilometers per hour. Okay, so if you buy a scooter, you need to ask the person 2 questions. What is the power? And maximum is this. And what is the speed?
Okay.
And the maximum is this. Because if you have more powerful than 250 watts or more speed than 25, the Gardaí, the police can take this from you. Okay? So just be careful with that, right? 250 and 25.
Policeman
Yeah,
will.
take it.
Oh, it
Yeah.
is illegal.
Yeah, here it is.
It's more than 250.
Yes, correct, yeah. The same for bicycle, electric bicycle.
Oh.
Because what happens is a lot of people here, they buy it from America. And in America, it's 350 watts. And they're not supposed to use this.
Says here, before when I live in Barbary, there's a lot of people take it on the train.
Yeah, I did. I used to take, when I lived in Skerries, I used to take it on the train.
So if I got this one, I won't pay the money for the traffic.
Yeah, that's why I did it too. So I would use it down to the train station. Or, no, sorry, down to the bus stop, a custom house, beside the train station. But mine wasn't electric. No electricity. I had a normal one.
Is that quick? The normal one?
Yeah, but it makes you tired.
Yeah.
Makes you tired, yeah, it's tired.
Electric.
Electric one is nice. I think there's a good website you should check. I think it's called something like Tom Top or something like this.
Tom. Okay.
Something like this. They have it.
Maybe it's possible. I bought a normal one and I gave my uncle. He can change to electric one. 'Cause he changed the normal bicycle to
electric, did he? Okay, good.
Maybe it's possible. I don't know. So I'm not really good at this kind of.
No, I don't think you can change it. I think you need to buy it. Yeah. Okay, so we'll continue anyway. So just remember 250 watts maximum, okay? Now, you might be wondering why this is true. You ready, Ben? So, you know Benjamin Franklin? American? He's the guy who used to fly the kite in the storm. The problem is this. Yeah, you know the story. And he had the key.
Copper?
Yeah, the copper key. The problem is this. You know the story? It doesn't matter. Yeah. The problem is we say electrons are negative. This is bad. It should have been electrons are positive. Do you understand? This is my left hand, this is my right hand. If I said this is my right hand and this is my left hand, if I swap them, that is okay as long as you do the same. You know, it's not like this is really left and this is really right. We just call this left and we call this right. But it could have been the other way. It's the same thing with the electron and the proton. We call it minus and we call it plus. But it could have been the other way. It doesn't matter. It should have been the other way. Because if it was the other way, then we would have electrons flow this way. And if we call that plus, then the current flows this way as well. The reason it's opposite is because we called the electron negative when it should have been called positive. Too late to change now. This is the problem. And this is because of Benjamin Franklin. So he called this thing negative, and then later we discovered it was the electron, and then we realized, oh, too late, we should have called it positive. So
Wait, thank you. Why thank you again?
well, it's thank you. You know, thank you. It's because we called electrons negative and protons positive. It would have been better the other way. It would have been much better the other way. So anyways, this is just a funny comic. This guy is coming back to the future, and he's trying to tell him, what you're doing is backwards. The one on the glass should be negative, whereas he called it positive. So it's just a little joke about this person. If he could travel through time, he would ask him to change it the other way around. So we can't, it's too late now. Okay, so let me see, how are we doing? Yeah, we've got time to continue with the small lesson. So you mentioned this word earlier, the amp. You said it as well, the ampere, A. And it's a current. And, oh, you're back, Khalifa. Okay. Now, the bad news is the definition of the amp is quite difficult. So this is the idea. You can get by? Imagine we have one wire here and one wire here, and the current flows, and the current flows. Okay, we say there's, oh, and sorry, the distance here is 1 meter. We say we have 1 amp here and 1 amp here if the force between them is equal to a certain number. I'll give you that number now. We have 1 amp if there's a force of 2 times 10 to the minus 7 newtons. If we have this much force between these two, we say we have an amp. So this definition is very difficult because it's not really a useful definition because this force is so small. So if I have 1 amp here and 1 amp here, there will be a force of this much. If I have this much force, I have an amp. Okay? So if we have 2 times 10 to the 7 newtons per meter of length between 2 straight, parallel, infinitely long, negligible cross-section placed 1 meter apart in a vacuum. Very difficult definition. So this has to be 1 meter, okay? This has to go off to infinity, okay? It has to be in a vacuum. You know what a vacuum means? No air. And the area here has to be 0 meters squared. You know, like a thin wire. So it's not, you know what I mean? It's not a real definition because you can't really do this. It's a technical definition, a mathematical definition. The good news is I've never seen them ask this definition in the exam. So that's good news. But I'd still would like you to write this down for your notes. It's good. So here's the picture here again, and this is how you can know if you have 1 amp, if you have this much force between the 2 wires. Like I said, it's a technical definition. It's not particularly helpful. Okay. Continue, Ben? Yeah? So, the next one is a much simpler definition. We call the unit of charge the Coulomb. So the Coulomb, symbol C, is the standard unit of charge. Now, so you know what I mean? Like, in chemistry you say an electron is -1, and you say a proton is +1. But these don't have any units. You know, like if I said to you it's -1 watt, +1 watt, like there's no units. So we measure units using the Coulomb. The Coulomb is the charge when you have 1 amp for 1 second. So, look here please. Imagine I have 1 amp. Okay? What that means is 1 amp is 1 Coulomb per 1 second. So every second you have a Coulomb of charge moving along. Okay? So 1 amp is 1 Coulomb per second. So that means 1 Coulomb is 1 amp for 1 second. You can make a Coulomb like this. Now, that's actually a lot. 1 Coulomb is a very big charge. Okay? It's huge charge, 1 Coulomb. It's not like a proton, it's a lot. It's a lot. So sometimes we measure it as like millicoulombs or microcoulombs. Coulomb is pretty big. Okay? So as a formula, the charge Q is equal to the current I multiplied by the time T. Q is the charge, I is the current, and T is the time. So charge equals current multiplied time. Oh, and this definition, you see the second sentence here. The Coulomb is the charge transported by a current of 1 amp in 1 second. That's what a Coulomb is. I've seen that in the exam many times. They ask you that many times in the exam. What is a Coulomb? A Coulomb is the charge transported by a current of 1 amp in 1 second. Is that okay? Yeah? Yeah? Is that okay, Ben?
So what's the unit?
Coulomb.
Oh, the unit is Coulomb.
Yeah, and then this is the charge. And the charge is in coulombs.
Okay.
Yeah. Okay? How big is 1 Coulomb of charge? It's rather big because, for example, 1 electron has a charge of 1.6 times 10 to the minus 19 coulombs, okay? So coulomb is a big unit because one electron is only 10 to the minus 19 coulombs. And we usually just write that as minus E for short. Yeah? And a proton then would be plus E. In chemistry you call it that minus 1. So in chemistry you say it's minus 1, which we say is minus E, which is this many coulombs. Now you'll need to write that value down. You'll need to...
We say E minus in chemistry.
You say E minus?
Yeah.
Oh no, E minus, yeah. That's different. That's different. Well, what do you say a proton is? E plus?
Just plus 1.
Yeah, it's a different thing. Okay, continue. What is the value that you need? Yeah? Right. I'll give you this question, guys. You have 100 milliamps in a copper wire for 2 seconds. What is the charge? So, for example, you have something like a wire like this, okay? You have 200 milliamps that flow, and it's made of copper, that's not important, and you look at it for 2 seconds, how much charge has gone through?
200.
No, be careful. Milliamps. So what is it?
2 plus
No?
turns.
No? Yeah? No. Oh, you're confusing. Look. No, look. Q equals IT. That's the formula. What's the I? The I is 0.1. 100 milli is 0.1. And what's the T? 2. So the answer is 0.2 coulombs. What's wrong? What's wrong?
Turn.
Huh?
Oh, okay. Maybe. Oh.
Yeah? It's okay? Are you sure?
Yeah.
Okay, write this down. So this question is 200 milliamps for 2 seconds. Thank you. I'm tired too. 100 milliamps for 2 seconds. Yeah? Okay, you got that? Right. What time are we at? Yeah, we'll finish. Can you do those 2 for homework? Because look, these questions are very short. So I think you can easily do this tonight. Home time.